Hello, guys. Welcome back. We are here to talk about something similar to the last thing we talked about, which was Ziegler-Natta polymerization. And this is called metallocene catalysis polymerization. There is a section in your book that you can read about this as well, but I think the Macro Galleria does a very, very nice job of explaining the basics of this, and I think in a little bit easier way to read. So, why is metallocene catalysis polymerization important? Well, much like Ziegler-Natta, it is a way that we can produce highly crystalline polymers as a result of getting specific tacticities. Remember, we said isotactic polymers and syndiotactic polymers are more regular arrangements stereochemically. Those can be, since they're more ordered, we can get crystalline arrangements that can oftentimes be spun into spun into fibers and made into really densely packed, strong items. And so I've mentioned the bulletproof vests before that are made out of polyethylene, right? Polyethylene's kind of funny. Branched polyethylene, atactically made through free radical methods. That's used for those little plastic Walmart bags. Metallocene catalysis polymerization can make iso and syndiotactic polyethylene. Very high density, very strong at stopping bullets. So, pretty cool. All right, so let's see how this works. All right, let's start off with the name, right? Metallocene. So, what in the heck is a metallocene? Well, let's go down here, and this is going to revisit something we talked a little about in organic chemistry. Do you remember when we used to talk about when we first introduced aromatic compounds, and we were introducing how to figure out if something was aromatic or non-aromatic or anti-aromatic, right? One of the examples we used was something called the cyclopentadienyl anion. That sounds pretty fancy schmancy, right? It's actually not, all right? This is cyclopentadiene, 5 carbon unit, 2 alternating double bonds, all right? And this is a non-aromatic species, and these two hydrogens are highly acidic here, right? We could pluck one of these off really easily, and what that does is that leaves a pair of electrons behind that can actually incorporate themselves into the ring and give you a delocalized aromatic arrangement. So this is an aromatic species, pretty stable, all right? And we showed this as one of the examples in OChem. All right. Overall negatively charged. Well, if you take 2 of these, right, you can take 2 cyclopentadienyl anions, and if you have the right metal atom, you can make a sandwich with them. Literally, just very analogous to a sandwich where you have bread, meat, bread. Well, the bread here is going to be 2 cyclopentadienyl anions, like this, and a metal ion that can form complexes with each of the negatively charged rings, right? So we're going to need something with, at least a positive 2 charge, and something like iron is really good for that, right? When iron makes a complex with these two rings, that produces a pretty commonly found species called a ferrocene. And ferrocenes are found in quite a few applications, right? We don't use ferrocenes for polymerizations, though. However, they're a good model for showing us what can happen. And this makes sense, right? You have negative charge, negative charge, -1, -1. They can both interact with a positive 2 very well. All right. So, but that's not really useful for us in metallocene catalysis polymerization. We're going to use a different type of metallocene besides a ferrocene. We are going to use something called, and I'm not going to say this right, I bet the first time, we'll see, zirconocene. Ooh, I did say it. Yay me. Zirconocenes. Zirconocenes use, instead of iron, they use zirconium. So yeah, hey, this is pretty cool. Going back to Ziegler-Natta, we saw we got to use some stuff that we haven't used before, really, in any of our classes. Titanium, vanadium. Now we get to incorporate zirconium. That's really neat. Anyway, zirconium's a little bit different. Number one, zirconium is a bigger atom. That's going to be important in just a second. And also, it's got a positive 4 charge, not a positive 2 charge. All right. So whenever zirconium forms a metallocene with 2 cyclopentadienyl anions, you're going to be left over with a positive 2 charge. So that means you have to have a couple of other ions in there to sort of balance things out. So one way that we can do this is to give the zirconium 2 chlorides, like this. So this is a nice little metallocene with zirconium at the base. In other words, a zirconocene, all right, called bischlorozirconocene. All right, and I mentioned number one, the size. Zirconium is a bigger is a bigger atom than iron, and also the chlorines, the extra ligands that you have in here attached to zirconium, they also take up room as well. They have volume, so they're going to take up space, right? Whereas iron fits together in a nice little sandwich like this, makes a nice little regular just arrangement. Sorry, I'm thirsty, so I'm drinking water in between. In a zirconocene, the 2 cyclopentadienyl anions, they kind of arrange themselves at a tilt, right, at an angle, sort of like this, while the rest of the middle sort of juts out. It's kind of like an Oreo that's been overfilled. All right. Never thought I'd use that analogy, but there you go. And it is this little tilt that allows us to use this species to make regularly arranged polymer chains, syndiotactic, isotactic polymers. Okay? All right, so there's actually some modifications that you can make to these cyclopentadienyl rings. You can make several different types of zirconocenes, right? You can put other stuff on them. When we use this to make polymers, we actually use derivatives of this that have oftentimes extra aromatic rings sort of fused to the side, sort of like in this one, right? You see an extra phenyl ring fused to each one of these cyclopentadienyl anions. Whenever you do this, this produces something called an indenyl ligand. Easy for me to say, right? Indenyl ligand. Got them right up here, and we also have included an ethylene bridge in between them. Right? So what this does is this gives, the purpose of this, it gives the zirconocene sort of a very, very specific window in which incoming monomers can be directed. Right? They can't just come in willy-nilly from any side. They have to come in a very certain manner. And it's that certain manner that allows us to get the regulation of tacticity. All right? All right. So let's see how this occurs. All right. Well, the first thing that happens is that we're going to add something that sort of helps things go along called MAO. This is short for methylamoxane. MAO, let's just say that, MAO is actually a polymer itself. And you can see it's got a bunch of aluminums in the repeat unit that have methyl groups kind of hanging down. Excuse me. And these methyl groups are going to be the really important part here, because the CLs that we originally have on our zirconium, they're not very stable. They're what we call labile. Labile means they have a tendency to sort of fall off that zirconium. You can kind of think of it this way. Cl- in organic chemistry, what was it oftentimes used as? Oftentimes used as a leaving group, right? Leaving groups are highly labile species, so the CLs tend to fall off. So what happens is when we add MAO, those labile CLs tend to get replaced with CH3 minuses off this backbone, right over here. The methyl groups themselves are kind of labile as well. So I'll be quite honest with you, I'm not exactly sure how they came up with this process, but it tends to work, so we're going to go with it. All right. The CH3s are also labile, not quite as much as the Cls. One of them, excuse me, one of them falls off of this species, and the other one forms sort of a new type of association or complex with the zirconium. All right, so follow me here. We got the zirconium, we have two methyl groups. One of them falls off, one of them remains. That's your CH3, and you can see the covalent bond is still there. You're also making a little bit of a complex between one of the methyl hydrogens and the now positive zirconium. Not a very strong one, but it's one that just keeps the overall integrity of the structure in place, keeps the methyl group aligned at a certain level. This is called an alpha agostic association. Very specific type of interaction that a metal ion, in this case a zirconium, makes with an adjacent methyl hydrogen. All right? And basically, what we have now we are primed and ready for an incoming monomer to actually start the polymerization. Right? All of this has been involved in sort of prepping the zirconocene to actually start the polymerization. All right? So at this point, you can have your monomer come in. Now again, this doesn't work well with just any type of vinyl monomer or any type of monomer. A lot of simple vinyl monomers work very well. Ethylene works well, as we mentioned. Propylene works well. And that's what we have here is propylene. All right. So basically what happens is whenever this propylene comes in with its carbon-carbon double bond, that's electron rich. Zirconium is positive, so you can form an interaction between the zirconium and your pi electrons. And that looks something kind of similar to what we looked at with Ziegler-Natta in the last round. Okay? All right, so we get into another one of these sections here. I'm going to skip the details about the metal complexation. You can feel free to look at it if you want to. But I'm going to go straight to the polymerization. All right, so here we have our complex. And once this complexes, you're going to have a bit of a reshuffling of electrons. Again, very similar to what we did with Ziegler-Natta. Okay? This carbon-carbon pi bond is going to break, and these electrons are going to form a full bond with your zirconium. And you can see that happens right here. At the same time, you're going to... Sorry, I lost my train of thought there for a second. At the same time, this zirconium is going to break away from this extra CH3 that it got from the MAO, right? This extra labile methyl group. It's going to break away from the zirconium, and it's going to attach itself to this end carbon of the monomer. And you can see the little arrows sort of promoting this electron movement, all right? So over here, zirconium, still positively charged, but now it's attached to the methyl of the monomer group. This methyl group is not detached from zirconium and is attached to the other methyl in your carbon-carbon double bond. All right? This alpha agostic association will break, and instead, zirconium will now form a new alpha agostic association with this carbon, or this hydrogen, CH, from the monomer, right? Excuse me. So what we've done is we've taken the carbon-carbon, the double bond, incorporated it here on the zirconium, and we've chunked that extra methyl group sort of on the end of it. And now, this is ready for another monomer to come in. Hey, here's another molecule of propylene. right? So it's going to do the same thing. This carbon-carbon double bond will break and form a bond with zirconium. Zirconium will break its bond with this carbon, and after the electrons shuffle around, you have another monomer incorporated into your chain. And you guys can look at this. Hopefully you guys are well versed with the macro Galleria. Definitely look at this page on your own and sort of work through it. I'm not, reciting the script here verbatim. You guys can look at it, but so I'm sort of hitting the high points. But yeah, this happens over and over and over again. Okay? This whole process produces an isotactic polymer. That means that the pendant groups, in this case the methyl groups, right here, like these guys, these are always going to be pointed on the same side of, they're always going to be pointed on the same side relative to each other, same side of the polymer backbone. Okay? The reason this happens is because of the complete design of this zirconocene, right? Remember we had something like this. These little extra six-membered rings, these indenyl groups, they basically sort of act as little overhangs that sort of prevent the monomers from coming in from a certain side. So, if the monomer comes in from the left side, in this case, like this, the methyl group has to be pointed away from this ring. If the monomer comes in from the other side, again, the methyl group has to be pointed in a certain direction to keep it away from this. And it's a little counterintuitive looking at it, but basically, in a nutshell, having these sort of oppositely arranged, directors, for lack of a better expression, helps to keep the pendant groups ending up on the same side in your polymer chain. So this produces an isotactic polymer. If we wanted to make a syndiotactic polymer where it alternated, we could just use a different indenyl group, right? And that's what we'd have in this example. This is a different zirconocene, right? This is where we have up here just basically a cyclopentadienyl anion, but here we have sort of a super indenyl group, right? It's got two rings on it. So the methyl groups, for example, if you're bringing in propylene, they'd be pointed one direction coming in from here and another one coming in from here. So depending on how you produce these zirconocenes will determine whether you get actually a syndiotactic or isotactic polymer. Okay. All right, I'm going to stop there and let you sort of wrap your heads around that, and we will keep pressing on, and I'll get some more stuff up later this week. This week we're going to get into anionic polymerizations, so that should be pretty cool as well. Until next time, have a good one. I'll talk to you later.